All right. Hello and welcome to PML School. Today we are starting with a new mini-series within our grand series of NonMEM NLME comparisons. So what I'm going to present over the next 3 sessions will be covering models for analysis of non-continuous categorical data. And as with all previous sessions, our focus will be on hands-on training. The ultimate goal is to provide some tips and tricks to our Phoenix user base. So I will explain in a step-by-step fashion how the original NonMEM code, the NM code, is translated into Phoenix PML code for Phoenix NLME. That's why the focus is on the hands-on exercises. That means that we won't be teaching the theoretical concepts that's behind these models. So far, in all the previous sessions, we have only dealt with modeling of continuous data, like concentrations over time or effects over time, like blood pressure, for example. Modeling of non-continuous data is a bit different, and you will easily see that this requires a more solid background in this specific modeling. Because at some point in time, you also want to better understand these types of models and their interpretations. At Certara, we do have Certara University that can help you gain this understanding. So Certara University offers advanced modeling courses, either as classroom courses as well as on-demand courses. And I will give you links to these resources at the end of my presentation. Now, when we start with today's session, as always, while I'm going through the presentation, if you have any comments or questions, please use the Q&A panel at the right-hand side of the WebEx console. So let's move on. Our typical agenda, starting with a model description, looking at the input data, and then do some exploratory data analysis, examining some plots, some plot outputs. And then at the heart of it, we will compare the individual lines of the NM code in NonMEM and compare that with the PML code in NLME. This is followed by a demo where I walk you through the steps of setting up and running these models in Phoenix, both the NonMEM and the NLME model, and we will also compare the 2 outcomes. And then I will finish with a summary and the Q&A session. So this is, as I said in the beginning, this is a new type of model, and it's a probabilistic model where we want to model a binary outcome that is measured against increasing concentrations. So, for example, you can think of an adverse effect that is measured post-dose, and depending on the size of the dose, the probability to experience an adverse effect will vary. But the outcome will always be either 0, there was no adverse effect, or 1, there was an adverse effect observed. In this probabilistic model, there is no error model for this type, since we just want to calculate the probability that the adverse effect happened or not. We don't want to predict observations, so there is no residual error in this case. And that is why later on in NonMEM, we will have no sigma array, or in terms of PML code, there won't be an error statement. So as structural parameters, we've got C50 and gamma. And clinically, the C50 value is of primary interest, since it gives us the dose where we have a 50% probability of seeing an adverse effect. So we want to measure its variability across the population by estimating a random effect, where initially the variance set to 0.1. As an engine, and this is the first time we use it, we will use the Laplacian engine, which is recommended for this type of model. move on. So here's the input data for this. It's very simple. It looks like much like a typical PD input, ID, concentration, and response. So these three columns. The first one is obviously the subject ID. And then we have one column for the concentration CE. And finally, one column for the effect response, our ESP. And the major difference to traditional PD data is that in this column, you only see zeros and ones for the binary response. Let's move on. Here's the first plotter with all responses versus concentration, and there's not a lot you can see, right? I mean, we have lots of data points with a value of 0 across the concentration range, same for 1, right? So that's just a spread of this, and this doesn't tell us a lot. So we need to change that. So how about this? This looks much like a PD curve, right? Like a kind of sigmoidal curve. Okay, it's not logarithmic on the x-axis, but this already looks like a PD plot. And what you can do in order to get there is just run some descriptive stats on your data, and you can then plot the proportions of the individuals versus the effect, versus the concentration here on the x-axis. And this is coming directly out of the statistics. And so this is a typical sigmoidal curve, if you will, and we can already establish a few initial estimates for our model later on. The C50 value around 2. Obviously, you can also try to estimate the slope, the steepness of this curve, and get the gamma value. But let's do that in the demo session. Okay, moving on. Since it's a hands-on session, maybe it's good to know that you can easily also show the data in form of a box plot, where you just plot the different concentrations versus the response groups, response 0 and 1. You see here a distinct pattern in this box plot between these two. Moving on, coming now to the code. On the left, the NonMEM code, typically starting with the input, right? And so it reads in 3 columns, ID, CE, and response as a dependent variable, DV. We usually, on this right-hand side in PML code, we don't need to do that. Do I have a... do I have a... Sorry, I'm just looking for the pen. Laser pointer. Wait a second, laser pointer. Yeah. So in NLME, we typically don't read in input through the PML code. This is done through the interface, the graphical user interface. But here we read in this concentration CE through the covariate statement. And that's really a general trick. If you have some data in your input data set that you want to use later on in your modeling code, just use the covariate statement. It will be read in and will be available later on in any kind of equations or assignments. So this is the input. Then we come to the definition of the structural parameter, C50 gamma. As we said, C50 is expressed with a typical value, θ1, and the random effect, eta1, and a typical notation. The second parameter, gamma, is just a typical value, θ2, so no random effect here. And then we define the probability, and the probability is defined like a PD model with an Emacs model. So the probability is CE, the concentration raised to gamma, divided by C50 raised to gamma plus CE raised to gamma. So this is a probability calculation. And this corresponding code in PML, we use the ST-PALM statement and the same kind of formula, C50 equals theta 1 times E to the n eta 1, gamma equals theta 2, and then we have the probability defined much the same way. And now when we come to the definition of the predicted values for the probability, this is a code in NonMEM. And this actually makes already use of our observed values 0 or 1. So the first part of this summation is taken care of. The first observation, if it's observed, if response equals 1, then y, the predictor variable, becomes the probability that is defined here. And if it's 0, if the response is 0, then it becomes this probability 1 minus prop. And similar to in PML, here we are making use of the LL statement, the log likelihood statement, which has at least 2 arguments. The first one is just the observed input, C ops in this case. A little bit, it's not really an observed concentration, but anyway, let's stick with the original name, so C ops, the observed values. And then here the same kind of formula, C ops times a log prop. If C ops is 1, so the adverse effect is seen, then it's a log of the probability. And plus 1 minus C ops, if C ops is 0, this term will become, in effect, is a log 1 minus the probability. So it's either the first probability or the second one. And that's the same for NM-Tron and PML. Okay, moving on. Second part of the code dealing with just specification of fixed and random effects. The typical theta matrix here with lower boundaries for theta 1. Theta 1 is C50, and an initial estimate of 2. This is something we've seen already in one of the plots, in previous plots. And for the gamma theta 2, the lower boundary is 0.1 and initial estimate is 3. And this is something, a value you can also get from the plot. For the random effect, the omega matrix, we only have one random effect, eta 1, which is set to 0.1. On the right-hand side, PML code, fixed effects, we're using the fixF statements, and with theta 1 and theta 2 defined within these brackets. And here, with a vector notation, C, lower boundary, comma, initial estimate, comma, upper boundary. You see, this is typical in Phoenix NLME. We want to avoid setting any boundaries, so we leave that open and just set these initial estimates to 2 and 3, like we did for the NonMEM code. And the random effect is written as with a runF statement, where we have just the n eta, which is set to 0.1. Okay, then in NonMEM we have to specify the estimation method. Here we need to tell it that we don't want to predict an observation. We just want to calculate a likelihood. And for this we are using the Laplacian algorithm, or Laplacian method, with this number of iterations and so forth. In Phoenix, as you know, this is set through the graphical user interface under the run options, where the algorithm is, whenever you have categorical data, it will choose right away the Laplacian algorithms, because that's the preferred one. You can also use QRPEM, but for this first exercise, we just stick with Laplacian. And next. Okay, the demo. Let's go to the demo. Let me share my Phoenix screen. Okay, Cheryl, can you see my screen? Hello, Cheryl? I think let's continue. So this is my model. As we've seen, here's the data. There's 3 columns with the values, concentration, and responses. And what else do we have? We have the 2 codes. Here's the NMTran code that we just seen on the slides, and the corresponding PML code. Let's have a look at some of the plots. So this is, as we've seen, the concentration, the response versus the concentration, where we just see the binary outcomes. Then, in order to get some more real curve data, we can run a statistic where we summarize the response over the different concentration ranges. And that will lead to this kind of statistic that we can then display in this plot. And here we can already see, so we have at 0.5 response, we are coming down to a value of concentration of 2 units. Now we could also maybe take a few measurements for the slope, but this should be okay. Next one is just we are plotting we are creating a box plot where we look at CE and group by response, and then you get these nice, nicely separated boxes here out of this plot. All right, so let's come to the model. So in order to run the NonMEM data, we just link our data, input data, with a NonMEM shell. Just put it into the main workflow. Okay, so this is our model data. Then we need the control file, and we just take it from our code. So this is here. Next thing we need to do is, we don't need that. We don't need to generate time residual plots, so we need to switch this one off. And we also don't need to clear DV for this residuals, because we don't have any residuals. So we just see if the data is mapped okay. So we need to map here the response to the corresponding input and just run the NonMEM code. This will take a few seconds. You see here the progress shown in this window. And it's already done. So we have all the data now here, different control files. We have our theta, standard errors on theta. We have our omega for eta 1, omega standard errors. Okay, then there's not much we can look at right now. So let's do the same for the PML code. So we just create a Phoenix model in this case, put it into the workflow. And here we go to the model and need to change to the textual model. Edit model as textual. Just need to delete all the PK model stuff and take this stuff from our predefined code and put it in here. And that's it. So this is our code as we just went through this. We just need to do the mapping here. ID is ID, COPS is a response, and CE is the concentration. Then we switch to run options. You see it's already switching to Laplacian because model is not Gaussian. Just make this explicit. And that's it, so we can run the model. And this will also just take a few seconds, a few iterations till it's finished. Done. And here again, we've got the theta table, standard errors, omega, and overall. Typically what we do, we compare the results from these both programs. So I've prepared already this workflow where we just need to have some data links, right, where we link all the output from these two model objects and put it into this workflow. And then we'll compare the theta values here in this table. These are just some preparational steps, and you see, okay, the NLME and on the left and NonMEM on the right, and there are just tiny differences in the figures. Same we can do for the eta values, and here you can see, look at, for example, let's see, histogram of eta values across the data set right here, and omega as well. It's the omega table. Shrinkage is given in percentage in NONMEM, in NLME, it's just a fractional value. And last but not least, overall table with the -2 log likelihood, which is pretty close. Okay, that was the demo. Let's go back to the slides. So just as a summary, so we have the two tables, the theta table and the overall table, showing the closeness of the results. So you're really getting to the same endpoint, same with the eta histogram. So this demonstrates how similar the calculations are between the two programs. And with that, I'm finishing this, and we can move to our Q&A session. Cheryl, do we have any questions? Or?
No, I do not see any, Bernd.
All right, if that's, maybe you have some questions after the session, so I'm happy to take questions later on. Either you send it to me directly by email, or you can also post this in our LinkedIn group or on the forum. We are happy to answer any questions that you may have. So then maybe just a few information pieces before we close. First one, as I mentioned in the beginning, the Certara University. There's lots of, as I said, the theoretical concepts to better understand and interpret these kind of models. I would rather encourage you to take one of those advanced PKPD courses where you see some outcome. It's not only with binary PD outcomes, but there are lots of topics that are really covered in this course, either as classroom course or as on-demand course, and you will get to this through the Certara University link. Next, yep.
We do have a question. Would you like to take it?
Yes, why not? Yeah, sure.
Thomas says, could you show some fits, F-I-T-S?
Fits, actually, we are not doing really fits. I mean, we are just calculating the probability. It's not a real deterministic model in the case, that we have gone through so far. So I'm not sure what you want to see. Maybe this attendee, if you can send me an email or maybe post on the forum this question, we can dive into this in more detail. But I'm at this time, it's not clear what you want to get through by fits. But I'm open to this question. So let's do that maybe offline, and we'll post it later on to the LinkedIn group or the forum. All right. Sorry. But before I close, just one other, some other stuff. The next session is obviously in 2 weeks' time. So here we are going into a time-to-event example where we do the analysis, and we will also be covering simulation of this time-to-event data and create some Kaplan-Meier plots. And then if you want to stay up to date with our PML School, I would encourage you to use our LinkedIn group, because most of the events and also materials will be posted there. For all the events that are coming up, we still have our landing page on Certara.com. You can view upcoming events there, and you can register from there. With that, I'm at the end. Thank you for your interest, and goodbye, and you may disconnect now.